So today we are pleased to have our very own seminar organizer, Kevin Arlin, talking about gaps in the semantics of dependent type theory. Thanks, Kevin.
All right, thanks, Evan. Thanks for being here, everybody. So the story of this talk is that a few weeks ago, Owen and Chris were kind of converging on this GATLab project, which is an awesome update to the abilities of CatLab, our rhyming library, to model generalized algebraic theories, which I'll tell you much more about today. And Owen called me and Evan over and was like, man, this NLab description of GATs really doesn't seem to capture, for instance, two categories, which is an example we definitely want to capture. And long story short, we all got very confused, and I got down a big rabbit hole of trying to figure out what even is a GAT, let alone its semantics, and how do the answers to those questions relate to other streams in modern math, in particular dependent type theory, Martin-Löf type theory, eventually homotopy type theory. And I think I've got a plausible set of answers together with help from some papers Dana dug up. And so let's see what we think. If you would like to follow along in a really amazing independent, semi-independent way, you can go to the Berkeley seminar website right now and pull up my slides. And you can scroll around my slides, and then every time I move on this set of slides, it'll drag you back to where I am. So, yes?
I didn't dig anything. I just went to Google Scholar, and I happened to recognize the names of the authors.
Great.
So that's,
yeah, so data very easily found. Thanks for the correction. OK, so a little warm-up will be sort of more or less a review of Owen's seminar on algebraic theories from May. OK, so an algebraic theory, same thing as a Laver theory, ordinary finitary algebraic theory, has a syntax that looks like this. You're allowed to basically make these kinds of statements, and that notation looks normal if you like type theory, and if you don't, looks pretty mysterious. So there's an example here. You basically have some things that can have collections, and they can have terms in the context of some introduced variables. So this is the theory of a monoid with an action on it, phrased in this syntax. You've got some kind of thing M that has a thing E inside of it. Whenever you have an M and an N in M, you can multiply them. Whenever you have an M in M and an S in S, you can multiply those. And then there's some equations saying that you've got a monoid action. So that's a syntactic way of presenting a theory of a monoid action. It's got two different sorts because there's the monoid and the set. And that's pretty much all I'm going to say about the syntax there. Yeah.
Like when you look at the multiplication of mn, how do you read that?
This would be m times n in ordinary monoid notation. Oh, right. Yeah, I definitely need to do this. Yes. OK, this is an Owenism, I think, originally.
It comes from
Evanism? OK. Whoever's responsible, whoever we're blaming here. OK, it's more common to put the context on the left in type theory, but a lot of the time you kind of care about the output. So I'm putting the context on the right. So in context, that you have m and n in your monoid, you get a product of m and n. OK, or to read it left to right, you have a product of m and n whenever m and n are elements of your monoid.
So the reason we do this is that for a big theory, these context stacks they get really large, and they clutter up things. So it's kind of nice to put them at the end of the more interesting bit. Yeah.
Does that make sense? OK.
Yeah.
Cool. Any other questions on there? So this is some kind of thing whose models are supposed to be a monoid and a thing that monoid acts on. So speaking of that, semantics. You can model an algebraic theory like the one I just wrote the syntax of in any category that has finite products. So the syntax of your theory includes maybe some types. Those are going to be objects in C. So you have an object of C for your monoid, an object in C for your S that the monoid is going to act on. Actually, no, I don't have the example there yet. If you have a context of variables, so I've got some x and some y, that will be realized in terms of a product. Terms like the multiplication in your monoid become morphisms in your category, and equations are just equations. Let me actually go out of, yeah, I didn't write that out explicitly in terms of the monoid example. If you just write M and S for A and B, though, then that's the monoid example. So that's a kind of direct way of interpreting the syntax in a category. Here's a more high-minded, maybe, way of talking about the semantics of an algebraic theory. The idea is that out of this syntax of a particular algebraic theory, like a monoid action, you can build a category that has finite products that's built out of, well, that M and that S and finite products of those, and these things are going to be some kind of morphisms in your category. You can freely build a category with finite products purely out of the syntax of your theory. And I'll give a citation on the next slide to a book of Mike Shulman's that's really great for explaining how this works in a ton of detail. But a good way to think about this category you're generating is that its objects, morphisms, and relations actually are syntax. So like an object of this category is some way that you can prove using your basic types, say M and S, and the fact that you can take finite products, that some type exists, et cetera, et cetera. There's lots more to say there, but that's not the direction we're going today. So you can build a category with finite products out of your theory, such as for the theory of monoid actions. If you want to freely build a category with finite products out of that theory, you've got an object S and an object M, and you have finite products of M's and S's, including the empty finite product, so that'll be a terminal object. And you have morphisms for the operations in your theory, and also the derived operations. If you have any monoid acting on a set for the classical kind of model, then say you have like 3 elements of your monoid, you can multiply them all together and then have them act on your set. So this is called a derived operation. It has to be available anytime you have a monoid action, even though it's not explicitly listed in the syntax we started with. So we're thinking of the syntax we started with as a presentation for this category that has a whole bunch more stuff in it. Okay, and the big idea is that a model of the theory of monoid actions in a finite product category C is the same as a finite product functor out of this free guy F. Right, so we initially define monoid actions in terms of you choose an object M and you choose an object F and you choose a morphism M by S to S and blah, 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 blah. It's kind of manual and closely tied to the syntax. The upshot of all this is you can define models of algebraic theories as functors of finite product categories. And that's it. And that's something that we know what that is and doesn't depend on syntax. And so it gives us a much clearer description, at least for the categorically minded, of what a model is than the more syntactic version. Okay, so what did we just do there? We've got some kind of a type theory. I was working on the type theory of algebraic theories just now, where you can have types and terms. The categorical semantics program for any given type theory, maybe be fair to say, is you say, what kind of category can I model that sort of theory in, finite product category in this case, and then can I build that sort of category out of the syntax of this theory? And if so, then you have kind of a purely categorical characterization of what it means to have models of this kind of theory. Okay, so this is the warm-up. It's a little quick, probably. Anything I can try to clarify there before I say it all again with a G in front of it? And a little slower. Oh, yeah, okay. But that is way smaller than expected. But there are some citations way down there. Let me say, yeah, Owen gave a talk on algebraic theories a few months ago, and Mike Schulman has an incomplete but fantastic book on basically exactly building cool gadgets out of syntax called Categorical Logic from a Categorical Point of View that you should look at if you haven't. And you can see what's actually going on here. You wanted to see this again, Priya? No, it's an isomorphism problem. Yeah.
What if we started with Boolean algebras? What would we get out of it?
So Boolean algebras will correspond to classical propositional logic. So you are in a kind of unitype situation. You just have terms, and maybe you can take conjunctions and terms and things like that. So yeah, this all is happening up a level from propositional logic that lives in Boolean algebras, or maybe hiding algebras if you want, intuitionistic.
No? I think, I don't know exactly what you're asking, but like there is an algebraic theory of Boolean algebras.
That's also true.
And so you can consider Boolean algebras internal to C.
Yes, right. So Boolean algebras are the semantics of theories in classical propositional logic, or, depending on what the question meant, also there is an algebraic theory whose models in a finite product category, C, are Boolean algebras in C.
What are Boolean algebras about?
Say again?
Is there a sense of what that means to have a Boolean algebra arbitrary finite?
Well, you've got an object, and there's some binary operation that has the universal property of conjunction, and some binary operation. Maybe it's.
Well, it doesn't necessarily have a universal property.
It has equation. Yeah.
It's a ring. It's an idempotent ring with negation.
I think we're going a bit far afield.
Yeah, anyway.
But I guess
Yeah.
one question, is there one sentence which was like, Boolean algebras in group blah.
Oh, there probably aren't any in group. Boolean algebras in set are Boolean algebras.
Okay, sure.
Such sentences are always true. But yeah, so this is like the beginning of sort of what it would look like in a category. And it turns out it's equational, so you don't have to explain these things in universal properties, and that's why there's an algebraic theory of it. Yeah, Shava?
On your next slide, you mentioned the word gadget. Is it a formal thing?
The word gadget is intended to be maximally non-formal. Some sort of thing that,
Non-formal.
yeah. That's a,
Because you say the initial gadgets, Schulman's.
yeah, these are supposed to pattern match, and that's it. Something goes in there.
A category with some extra structure to be specified.
This is like the C preprocessor. Like
I'll give you one.
Okay. This is like using the C preprocessor for category theory. You just like find and replace gadget with something else.
With literally anything that maybe is a category at all in any sense. Okay, cool. Thanks for the questions. Hopefully that's feeling a little bit nicer. So onward to GATS. The only thing that changes in generalized algebraic theories, by adding some dependent types. So in an algebraic theory, you've got just a thing M and a thing S. But you can't say for every x in M, I get some other thing A of x. That's what you can start saying in generalized algebraic theories. So this is the example that I'll come back to in a few different ways. There's a generalized algebraic theory for two categories, since that question kind of inspired this talk. So what is in that theory? There's some type ob. I should have said ob type there. So let me know if I'm missing any decorations or inconsistent about my decorations. So there's some type ob that's going to be the set of objects of your two category, or the thing of objects of your two category. For every two terms of ob, there's some homs. That's the one homs. For every two terms of ob and two terms of the hom from between those two terms, which is a dependent type appearing in the context, you have a set of two morphisms between those two terms. And then there's lots of operators and equations saying I can compose one morphisms, I can vertically compose two morphisms, horizontally compose two morphisms, associativity, unitality, interchange. It's a long theory to write all the way out. but that is the start of that theory. This right here should say HOM2. I'm writing HOM2 for two morphisms to distinguish them. So this is the sort of thing that we can start doing in GATS, and there's no way to do it in a plain algebraic theory. There are other approaches than GATS, but plain algebraic theories will not allow you to model something like a two-category. So that's how we're upgrading. And this kind of syntax is going to have some notion of model, such that a model of this theory in set is a two-category, maybe a small two-category. And then we can also model it in some sort of other contexts. Okay, but so getting back to the gadget question, I wasn't there in 1963 or whatever, but it seems very plausible that finite product categories are the place to model algebraic theories. For me, again, at least it's not at all clear where you can model a GAT. So to be in a category that can model a GAT, you need to have some notion of an object of that category that depends on terms of some other object of that category. What do any of these words mean? It's basically you have types in your theory, and those are probably going to be objects of your categories. But then there's dependent types, and there are terms, and it's not obvious what those should be in a category. One standard answer, which I won't say too much about, is to say like, oh, you put all the HOMs together into one big object. So here's all the HOMs in my category, and it's got a source morphism and a target morphism. And then if you've got some pullbacks in your category, you can define the domain of composition. So this story interprets dependent types. This type HOM depends on two terms of ob. It interprets that dependent type in terms of morphisms into the type being depended on, which is common and plausible and works well in set, but is not quite the right, or at least not quite the only option. So the notion of dependent type in set, or what HOM looks like in set, is if you've got a set X of objects of your category or two category, then the way that you intuitively as a mathematician think about this dependent type, HOM, which gives you a set for every two elements of the set of objects, the way you think about that is literally for every two elements of the set of objects, you get a set of HOMs. You, I claim, I mean, I know I'm putting a lot of thoughts in your head, but I claim you never conceptualize the collection of all the HOMs at once in your category. You just think about HOM x, y for some fixed x and y. And so this, in set, this kind of notion, a choice of a set for every two elements of x, is equivalent to this kind of notion, a collection of all those sets and two functions down into ob. But equivalent is a tricky word, and they're not quite the same. And in other categories, as I said in a way that almost fits on the slide down there, in other categories, we might not be able to move between this sort of notion, a more naive notion of dependent type, and this sort of notion in the same way. So this is not the notion of semantics of GATS that we're going to be happy with. It's not what we use in CATLab or GATLab, and we want something that has the notion of dependency a little more natively.
Okay,
Yeah.
not that relevant a question, but when you say family of notions depend, I understand you're saying there's two different notions of HOM in set that happen to coincide in set.
Yeah.
One of them you're calling an arrow, one of them you're calling a family of objects dependent on an object. That's the first one you're calling a family of objects, and the second one you're calling arrow. So
Sure, yeah.
so an arrow in this definition is a function from op times op to C. Don't say C yet, because God knows what that's going to mean for an arbitrary C. But for set,
we have a notion where to give all the Homs in a category is to give a function from ob cross ob to set.
And that's your notion of an arrow.
No, that's the notion of all the arrows, right?
But,
So if
how using this terminology here on the last sentence, I guess. What do you mean by
an arrow, I mean this.
Okay.
Yeah. So this you could call the indexed version of a set depending on a set. This you could call the fibered version. So yeah, when I say an arrow, I mean the fibered version.
Okay.
Thanks. Anything else I can clarify or muse upon?
So you're saying there are two equivalent notions of arrows that in the category of set.
Two equivalent notions of dependent types, I would say, or of sets depending on another set. Either a function into like the class of all sets, or collecting all of those sets into a single set over the domain. Perhaps it would be good to make sure we're clear what exactly that correspondence is. If you have something like that, which is a collection of sets A of u for every u in u, that corresponds to the arrow to the fibered family of sets where A bar is just the disjoint union of all of those A of u's. Right? You take all the values of this function in a set, disjoint union them, and there's a projection that sends A of u down to u. Okay, so that's like the simplest case of the Grothendieck construction, if you've heard that phrase, and we have it available for set, but set's pretty special in that way that like we have basically a notion of the set of sets, modulo mutter mutter. And in an arbitrary category, you're not going to have that notion. You're not going to have some kind of Grothendieck construction available. Anything else? Okay, so what are the semantics of GATS then? There are actually many answers to this question. I have evidence that I'm not the only one who finds this a little mysterious. John Cartmell, to whom GATS are due, I think I cited him when I introduced them, also introduced the first two notions of the semantics of GATS, called categories with attributes and contextual categories. He's now back to research and continuing to argue for contextual categories, and they've had a pretty successful life since he invented them, including in Voevodsky's work on homotopy type theory. But I'm going to go with a variant of categories with attributes today called categories with families. Okay, just a bunch of background. I'm going to talk about categories with families. That's a notion that's due to Dybjer. If my Swedish is on point there. Anybody wants to help with the Swedish, feel free. And here's roughly what it is. Okay, so this is going to be a kind of category where I can model GATS. So I need to have some notion of context. I need to have some notion of type. I need to have some notion of term. So I literally just basically say those things. I've got some category C. I feel like my category C consists of contexts in some sense. For every context, I have a set of types in that context. For every type in a context, I have a set of terms of that type in that context. And okay, C is a category, so how do the morphisms relate to the types and the terms? There's a functor that we think of as substituting. We think of morphisms as substitutions. And the operation of substitution lets us move contravariantly and functorially between types and terms in different contexts. So that's half the definition. It's a slightly elaborate concept, but the basic idea is you've got a category of contexts. Each context has a set of types. Each type has a set of terms. And those are all the things that exist in a GAT, so probably we're going to be able to talk about GATs in a category with families. The families are the family of all the types and all the terms in that type in the context. Right, yeah. Types, yeah. Yeah, so yeah.
Types, or is it all the types that you can construct out of context?
Tie of C is going to be thought of as all the types I can construct in that context. Everything that I can say in context gamma A is a type. And the types and contexts are strictly separated right here, which they aren't a lot of the time. A lot of the time, we're kind of, in different models, we're kind of woolly about types being basically the same as contexts. But this, I think, an advantage of this presentation in terms of categories with families is that we really separate the three notions of context, type, and term out. And then we're going to have to woolily squeeze them back together later, but at least we can start that way. I'm going to pronounce that abbreviation, if it comes to it, CWF as CUV, because I think Welsh is the only language you can pronounce that word in, so I'll say it in Welsh. Owen?
Maybe you'll get to this later, but something that I've always found very unsatisfying about categories and families, that they don't seem very slick.
Do you mean because the definition is so long?
Yeah.
Yeah, because this isn't the whole thing.
There's a set, blah, blah, blah.
Well, you can do a little better with this. You can say types and ty and tum. These two functors fit together into a presheaf of families of sets on C. Right, where a family of sets is just that. And so that compacts things a little bit.
A presheaf of types, and then for each, I'm not sure I quite understand.
So for each context, C, you have a family of sets
Oh, I see.
which I feel like it's going to be confusing not to write in the fibered way.
Yeah, okay.
And that's a presheaf into the category of families. Yes, but that's still only part of the definition. I think the like more meta answer to that is I don't think there's any real slick definition of a thing where you can give the semantics of a cat based on everything I've seen looking into it, which is interesting. Okay.
So you're saying
Yeah.
it doesn't assign set for every context, for every object in the category?
Yes, part of giving a category with families is to choose some set of types for every object of that category, and for every element of that set, choose some set of terms. Context, type, term are just meaningless words here, right? For every object, you get some set. For every element of that set, you get some set.
Yeah, okay.
And they vary. It's just a vibe, nothing formal.
Okay.
Hence the scare quotes.
Is that a formal word?
It is not. Also not a formal word. I'm really getting killed here on obviously informal words.
Do you have a favorite example?
Yes. The key example of a coup is indeed the presheaf of types sends a set to the set of all sets dependent on that that set. So you can either have functions A from X to set, or, as we saw with that Grothendieck deconstruction, sets over X. And that, in this case, is maybe a more intuitive way for some of us to think about a type dependent on X, some kind of maybe a bundle over X. A term of type A in context X is just a choice of an element of each of the AXs, which corresponds to a section of that function under the Grothendieck deconstruction. Okay, I think I'm happy there. Brendan? No, okay. Right. So then this example is describing how, is getting towards how we're going to think of a two-category as a model of the theory of two categories in the CUV set. So you've got some object of set corresponding to the set of objects of your two category. You've got some type depending on two objects. That gives you the one HOMs. You've got this horrific type over, what is that? This is the collection of all pairs of an arrow from X to Y and an arrow from Y to Z, varying over all X, Y, and Z. So that crazy context there is just the set of all things like this, all situations like this. There's a type in that context that at some x, y, z, f, and g gives you the set of all hums from x to z, and there's a section of that type or a term of that type that gives you the composition of any two one morphisms. Right, we said to choose a term of a type, we just have to choose some element of each one of those things. Given any x, y, z, f from x to y, g from y to z, we know we can choose something from x to z, or we want to be able to, given by the composition. So composition is a term of some crazy dependent type in the cube of sets. And similarly for getting the type of two hums and composition, blah, blah, blah. Trying to be completely explicit about these things in a cube of set gets pretty rough pretty fast.
You haven't defined the sigma formation.
Yeah, I mean, if you don't like the letter sigma, I just mean disjoint union. So this is literally the set of all pairs of two parallel one morphisms.
So wait, are we? Oh.
Yeah, because this is completely just in set.
Oh,
And I don't really know how to say what set this is, right? Yeah, we're in set. This is vaguely related to what will happen in an arbitrary category. But when I'm writing sum or disjoint union, I'm really using the we're in set. And I can build a context out of any set that I can put together. Cool, anything else? Yeah, as I said, amazingly, we haven't defined a cube yet. This context is problematic if you think a cube is just a category with sets of types and sets of terms. So let's look into that. We don't know how to build a context like that in an arbitrary cube. What we can kind of think about all of those things as in an arbitrary cube so far are, well, you've got some context, some object in C, and you have some set of types in context X that just live somewhere else. That's just a set. And, or X cross X, I guess, for hom. And there's an element of that set called hom. We need some way to pull this type in context X back down into the category of context, or we're not going to be able to have all that stuff be a context. So basically, hopefully, we can pretty much get away with that being this whole slide. There's a bunch more that you could see if you really wanted to. Let's see if there's anything I definitely want to say here. If you have a type in some context gamma, you can extend that context by that type to get a new context. That's probably what I really want to say here. What I unwisely went to the trouble of putting in there is a proof of something about pullbacks that we're going to in the next slide, so feel free to just ignore that, but maybe it'll be fun to look at later. So this is giving us a connection between these two universes, letting us pull types in a context down to build a new context. That's something we need to be able to do to build a context like that one for the two homs. Okay, so that computation that I certainly didn't talk through on the previous slides means that there are certain pullbacks in a category with families necessitated by the existence of context extensions. Specifically, if you have some type A in context gamma, and you look at its extension, which comes with a projection back to gamma, and you have some substitution into gamma, and you try pulling back A over to delta using just the functorial substitution. So gamma star of A is a type over delta. It still lives somewhere else. OK, we can bring it back down by extending delta by that type in context delta. What I didn't prove, but it's on the slides, is that this thing is always a pullback in your cube. And those pullbacks are like very central to type theory. That's a very salient, meaningful thing if you do a lot of type theory. And a a surprisingly critical technical detail about pullbacks like this that come from pulling back a context extension along substitution is that they are strictly functorial in the bottom row. If you build this particular pullback square using gamma and this particular one using delta, that's exactly the same as building the particular pullback square for the composition of gamma with delta. And the upshot is cubes have some really nice pullbacks in them that behave in a way that pullbacks don't usually want to behave. Pullbacks are defined by a universal property. So you may know that if you stick two pullbacks together, you always get some pullback. But then if you choose all your pullbacks to begin with, all that means is that this pasting is going to be isomorphic to that, canonically isomorphic. But because when you like substitute some syntactic expression and then another one, there's no way to tell whether you've done two steps or just one step. Just because of the nature of syntax, these pullbacks have to be strictly functorial in a cube, and that is probably sounds like angels on pinheads when you first hear about it, but it's actually a huge issue in finding other categories that can model GATs and finding other natural examples of cubes. So we can choose nice pullbacks like that in the cube of a set, specifically because we have this notion of a set depending on another set that is indexed, that is not a function like that. The way that people like to try to give categories that can model dependent types is to start with some category and say, okay, a family of things over X is just a morphism into X, right? Picture's gone. And then give substitutions in terms of pullbacks. And so there's some coherence issue that that's not quite right because things are only going to be isomorphic and you won't be able to directly interpret the syntax of GATs in that kind of situation. So the point of this is that it's surprisingly hard to give natural, like familiar categories a cube structure. That's mainly getting into just stuff that occupies type theorist lives. It's a little bit off to the side for today, but it's a surprisingly big deal. Okay, so modeling GATs and cubes, I sort of kind of already said what this looks like in set. And now if you're in any cube, you can have a two category internal to that cube. You've got a context, an object, which is the object of objects of your two category. You've got a dependent type of Hams. You've got an even more dependent type of two Hams, and you have a whole bunch more stuff. But so if you put 5 slides of requirements all together, then you would have a notion of a two category internal to a cube. And the same story, hand wave, hand wave, hand wave, works for any GAT and explains how you can model any GAT in any cube. So cubes are our proposed notion of a thing that can have the semantics of a GAT. So these dots are context extensions, as I didn't go very quickly there. And there is a variable free notation that can sort of be used.
So what's that, pi?
That's the projection out of a context extension. It probably isn't really worth explaining without spending more time on that. But there is a way to, you can switch between this nonsensical notation with no variables and a notation that has variables, more like the actual syntax of GAT. So you don't have to worry about that unless you're going to prove theorems in this area. You can build contexts that look like the context you need for two categories. Okay, so cubes can model GATs. Cool. There's an initiality theorem for this. You can build a cube out of a GAT. You can build the free cube containing a two category out of the syntax of the theory of two categories. This all says exactly the same thing as I said for ATs, just with G's in front and cubes instead of Cartesian categories. So the categorical semantics story for GATs with cubes is exactly as good as it is for ATs with Cartesian categories. So that's great. We can say a model of a GAT is a morphism of cubes, which I didn't define, but you could guess if you really wanted Yeah.
Instead of set, could we use a topos?
Is every topos a cube? The problem is to get a notion internal to the topos, an object of the topos that looks like that topos being internal to itself, right? The set of small sets lives inside of set. If you have some topos E, there's not necessarily like a model, a picture of E inside of E.
Okay, rotate topos.
I mean, the actual answer is yes, but you have to do a bunch of work. And you don't quite need a topos. You can do this in any locally Cartesian closed category, but the coherence theorem takes some work. Mm-hmm.
Yeah, can you do this in any Cartesian closed category with a notion of universe?
Right. So to try to do this in a
Like,
topos or something more directly, you're starting to think about universe types, and yeah, basically, there's probably some kind of this is what universes are basically for, is to give you a direct notion inside some other category of that.
Yeah. Okay.
Yeah. So I'm not going to actually say anything about universes, but yeah. Right, and so, okay, we can build a cube out of the theory of two categories. It's got all of the objects and morphisms that you need to have a two-category inside a cube. Okay, so that's just summarizing that section. Any GAT can be modeled in a cube. In fact, it generates the initial cube that has a model of it in terms of its syntax. And actually, I was extremely loosey-goosey about what exactly the definition of a GAT is, right? And in fact, it's really annoying to be completely precise about giving a syntactic definition of a GAT. And not everybody agrees about what it is. There's variations in syntax. So there's this really cool paper that I'm citing here that defines what a GAT is by building up the notion of a cube with a model of that GAT in recursion with, you make your GAT bigger, you make the notion of cube with a model of it bigger, one step at a time. So these guys actually define the GAT sigma as the initial cube with a model of sigma. For what it's worth, it's pretty cute. And you can get away without doing any syntax, which is fun in math, maybe not so useful in GATLab. So in this perspective, syntax is really just a way to construct initial gadgets. And it's not actually necessary for defining stuff. It's kind of fun. Okay, that's the bulk of the talk. I'm going to say a couple words about how this relates to dependent type theory more generally, if I may. And
What do you want to do with it next? What do you want to do with it next?
Most of what we're interested in GATS now, I think, is in software. And so the goal of this was to understand better what exactly it is we're implementing and how it relates to, as is coming in the next couple of slides, to more general dependent type theory. So I don't myself have goals to, say, do mathematical research in this area, at least not right now. But I do have goals to implement this stuff on a computer. Thanks. Yeah.
I'm familiar with all these natural models.
Sorry, there was a motorcycle again.
I'm familiar with Steve Aldi's natural models of type theory.
Yeah, that's another notion of semantics of dependent type theory. It's some slightly different thing.
I see. Are you familiar with whether that's equivalent to the pool stuff or?
I think that they're all probably kind of supposed to be equivalent, but the problem with that is that a lot of the time type theorists are assuming that you have a bunch of decorations I haven't mentioned yet, like sigma types and identity types and pi types, to do real proper type theory. And so GATs are so stripped down that cubes could be more general. Yeah, yeah. Okay, so what's the connection with actual dependent type theory? Long story short, in full-on dependent type theory, you can not only have types that depend on a term of some other type, you can have type constructors that take in some arbitrary types and give you a new type. So the constructor that gives you function types is a key example. Coming in just a second. There is a GAT whose models are Cartesian closed category objects, but there's not a GAT that can tell you the cube I'm modeling this in needs to be Cartesian closed. So you have to actually add extra powers to your syntax to be able to insist that models only happen in Cartesian closed categories. So you can say things like this in proper type theory, which you just cannot say in a GAT. So in models, what this means is I'm modeling this all in some cube, and for any two objects of that cube, any two contexts, I have some function type that's a new context. So this kind of operation is the decoration that starts us moving from GATs to full-on dependent type theory. And similarly for pi types and sigma types and identity types and universe types, all of these are decorations beyond the syntax of a plain GAT that say I'm going to have extra structure on the cube that I'm working in to be able to model all this stuff. So once you start saying you want this to be true, you can only model theories that include that rule in a Cartesian closed cube. Talk to somebody who cares about that later, given the emojis on it. This is an interesting point, but I think I probably can't get it across in the time and energy I've got now. Feel free to ask me about it afterward. So what GATs are is just the absolute skeleton of dependent type theory. The least you possibly need to be able to talk about some notion of like a thing where there are dependent types. So understanding the semantics of GATs in terms of cubes is, from one perspective, the first step to fully understanding the semantics of Martin-Löf type theory or homotopy type theory, which are based on some much richer syntax that has lots of type constructors that let you do other things. That's the point I didn't quite make. There's some very cool microcosm principle that I just think is not healthy to try to say right now. And yeah, to reiterate from the beginning, our cat lab is really based in large part around the idea that GATs produce good data structures, and Owen and Chris have been improving that. And I think that is all I will say. Thank you. Questions, comments? Yeah.
So one of the big points of functorial semantics is being able to look at semantics in categories other than set.
Yeah.
So I was wondering whether in the course of your explorations you found some interesting cubes that aren't set.
Yeah, so that's kind of relevant to the connection to eats. So there's a good theorem here that finitely complete categories are the same thing as cubes that have just a little bit of extra decoration. So you can build a cube out of any finitely complete category. It's not quite a completely general cube, but it is the most general one not built out of syntax that I can give an example of.
That's interesting. So
yeah.
You could, in principle, interpret GATs in something that actually is not quite as good as or not quite as expressive as a finitely complete.
Yes. Yeah. So the conclusion, and I'm pretty sure I've got straight on this slide, is GATs are just a little more general than essentially algebraic theories, although maybe only in a totally angels on pinhead sense, because you maybe don't care about cubes that aren't actually finitely complete, but maybe you do. Yeah.
Kind of reminds me of the difference between an internal and an enriched category.
Internal categories are models of an essentially algebraic theory, and enriched categories are models of a GAT, and then if you want to model them in an arbitrary symmetric monodal category. Symmetric monodal category isn't really a cube, but you can sort of wiggle around this. Anyway, yeah, I agree. Is there anything else?
How do contextual categories come into the picture?
Contextual category, in short, is basically a cube where the objects come with a filtration by integer lengths, so that they really feel very strictly like a context that's like x and a, y and b. That's a length 2 object. So it's an even stricter structure on the coup that ties it closer to the syntax. But they're the same-ish as all these notions are. You can build a contextual category out of a coup.
Is there a reason to pick between the two?
Cubes are, I think, in a pretty happy spot of having a comprehensible connection to the syntax while also having a definition that's pretty categorical. In particular, the stuff that I didn't try to squeeze in at 10 minutes too is that like there is a GAT of cubes. So you can have a cube object in a cube. So that's the microcosm principle I was saying. That's nice. Cartmell actually has published arguing that there probably is a GAT of contextual categories, but I think it's maybe not entirely clear. Other authors have claimed they think there's not. Cool. Will that do it? Okay, thanks.